All right. Hi, everyone. My name is Marta, and I'm a software engineer on the Stellar core team. And today I'm here to talk to you about the Stellar Consensus Protocol. We're briefly going to go over the agenda. So first, we're going to have some motivation for this talk. Why are we even doing this? And what are the things that we're going to cover? We're then going to have a quick recap on quorums and what they are and what they mean in the context of the Stellar network. We will talk a little bit about statements, which are the building blocks of the Stellar Consensus Protocol, and then we will see how statements are used in the process called federated voting. We will have a demo for federated voting to see kind of how it all plays out. And then finally, the two steps of the Stellar Consensus Protocol, which are the nomination protocol and the ballot protocol, will be the last thing that we will cover. All right, well, let's start with motivation. Why are we even doing this? So distributed consensus protocol are difficult to understand. There are a lot of steps, a lot of things to keep in mind. And if you're new to the protocol and just trying to get an understanding of it, it could be quite overwhelming to read through all those materials and try to understand everything at once. We also realized that there's quite a bit of advanced material out there, and there's a lack of simplified version. So this talk will not have any complex theorems, no math, just the high level ideas to help you get the right understanding of the Stellar Consensus Protocol. And we were inspired by physics. In physics, you don't go directly into complex formulas. You first get a high level understanding of what's going on. You try to imagine something before you actually go and work out the formulas and dive into more complexity. With that, we're going to briefly go over quorums. So you might already be familiar with quorums, but we're going to go over a few important definitions here. So a quorum set is a set of nodes that you trust. So for example, if you look at the diagram on the right, we have 4 nodes, A, B, C, and D, and you can look at the arrows, and the arrows represent the quorum sets. So for example, for A has B and C in its quorum set. Another example is for B. B has 3 nodes in its quorum set. It's A, C, and D. We also have the notion of threshold, and threshold is a minimum number of nodes in one's quorum set that must agree. For example, if we go back to our node B, remember that it has nodes A, C, and D in its quorum set. Suppose that the threshold for B is 2, which means that any combination of 2 nodes would be sufficient for B to proceed. And in this case, like I was saying, it can be any combination, so it can be AC, CD, or AD. So those subsets, AC, CD, and AD, are called quorum slices. And finally, the most important definition is the definition of quorum. Quorum is a non-empty set of nodes that contains a slice for each member. So in our example on the right, let's try and see if we can get a quorum starting with a node A. So remember that A has B and C in its quorum slices. So we add A, B, and C to a quorum, but ABC is not a quorum on its own because B and C also have D in their quorum slices. So we have to add D to the quorum. And then altogether, A, B, C, and D is a quorum. Another very crucial definition on the Stellar network is notion of nodes blocking sets. Any set of nodes in the quorum set without which the node cannot reach consensus is a blocking set. And intuitively, if you think about the name, the blocking set blocks consensus. If you do not see agreement of your blocking set, then you may not proceed in the consensus round, so you're blocked. Just with a small example here, if we have a quorum set of 4 nodes, and then suppose we have a threshold 3, so we require 3 out of 4 to agree, any 2 nodes would be blocking. And it sort of makes sense because we require 3 out of 4 nodes to agree. So if we have 2 nodes that are not in agreement, then they're blocking us and we cannot proceed and reach consensus. Another important thing here to note is that the concept of blocking set is a per node. Is per node because every node gets to select their quorum set, and so the blocking set for each node would be different depending of what their quorum set is. So going back to our example, let's look at the node C. So C has A, B, and D in its quorum set. And let's say that C went with the most aggressive threshold, 3 out of 3, everybody must agree. So any node really in C's quorum set can be blocking. For example, A is a blocking set because C requires threshold 3 out of 3. So as soon as A does not agree, C is blocked. Similarly, B on its own is a blocking set, and D on its own is a blocking set. And also any combination of those 3 nodes are also blocking sets, but here we're just looking at the smallest blocking sets. All right, moving on to statements. What is a statement? So statement is the smallest building block of the Stellar Consensus Protocol. It's basically something that the network wants to agree on. For example, when a node says, I propose this transaction set for ledger 5000, that's a statement. Or similarly, if the node says, I am ready to apply this transaction set for ledger 5000, that's also a valid statement. So the second one here is a little bit stronger because at this point, the node is actually ready to apply the transaction set, but nevertheless, both are valid statements, and both statements are valid for the network to agree on. Which naturally leads me to my next point. How does the network know if a statement is actually agreed on? It votes on it. And it votes on statements via this procedure that is called federated voting. So before we dive into the rules of federated voting, it's important to see how a node perceives a statement when it receives one. So a node may decide what it wants to do about a statement depending on what its quorum said about that particular statement. So for example, a node may say 4 things about a statement. It may say, I don't know anything about statement A, and I have no opinion whatsoever. It can also say, I received A, and it's valid, and I vote for A, but it's still not quite safe to act on it yet. So voting is basically like a weak form of agreement where a node says that, yes, I vote for A because I validated it, but we still don't know network-wide what's the state of A. A node may also say, I accept A if it has seen enough support in its quorum slice for this particular statement A. But at that point, the node still doesn't know if it's safe to act on it yet. And then finally, a node might say, I confirm A, and it is safe to act on it. Even if every node in the quorum slice has not yet confirmed A, they will not be able to confirm anything else but A. So this means that there is final agreement on statement A in the quorum slice. And at this point, a node might say, I confirm A. So these are the various steps that a node may take regarding a particular statement A. But let's actually go over the rules and see how this transition happens. How does a node vote for something? How does it move to accept and confirm? So here are the rules of federated voting. A node may vote for A if A is valid and consistent with previous votes. A node may accept A if either every node in its quorum slice voted for or accepted A, or a node's blocking set accepted A. And let's look at this second bullet a little bit closer. Why do we have this rule that a node may accept A if a blocking set accepted A? So remember the definition of the blocking set. Without the agreement of the blocking set, it is impossible to reach consensus. So a node has 2 choices. It can either be stuck because a blocking set accepted something else, or it might just go ahead and proceed and accept what blocking set accepted. And so this is why we have this rule here that a node may accept A if it sees the blocking set accepted A. But you might wonder, what happened if I voted against A before? In this case, a node may just forget its previous vote and accept A. Note that this does not mean that a node would vote for A. It could accept A, but doesn't necessarily vote for it. It could have voted for something else, but because it sees the agreement of its blocking set, it also accepts A. And then finally, a node may confirm A if every node in its quorum slice accepted A. All right, so I have a little demo here to see how those federated voting rules actually work in an example. So at the top right corner, there are the same rules of the federated voting that we just covered in the previous slide, but I just put them here like a little cheat sheet for us to kind of always be able to refer to it. So here we have a network of 7 nodes, and similarly to our previous example, the arrows show the quorum sets selected by each node. And I want to focus here on this dependency of node 5. So node 5 has 6, 7, and 1 in its quorum set. And it's important here because remember the definition of the blocking set. For this particular example, let's assume that the threshold is the most aggressive, right? So it's basically all nodes in the quorum slice must agree for a node to proceed. So 1 would be a blocking set for 5, and 6 on its own would be a blocking set for 5, and 7 would be a blocking set for 5. All right, let's move on to voting. So let's say that 2 different nodes on a network decided to vote for different things, different statements. So 3 voted for X, and then 6 voted for Y. And then those nodes send out messages saying that, hey, I voted for X, or hey, I voted for Y. And let's see what other nodes do when they receive those messages. So nodes 1, 2, and 4 receive vote for X from 3. And they have 3 in their quorum set. So they validate X, no problem with that. So they go ahead and vote for X. On the left side, nodes 5 and 7 receive messages from 6 that 6 votes for Y. They validate Y, no problem. And they also go ahead and vote for Y. Now let's refer to our second rule of federated voting, which is accept if quorum slice voted or accepted. So let's see what we have on the right side. On the right side, every node voted for X. So as soon as those messages get through, nodes may proceed and accept statement X. And so we can see that 1, 2, and 3 accepted X, and maybe some messages are delayed, and 4 hasn't accepted X yet, but this is just a matter of time where the messages reach 4. So something really important is happened here. If we look again at our node 5, remember that 1 is a blocking set for 5. And 1 just accepted X, and 5 voted for Y. Let's look at our rule number 3, which is accept if blocking set accepted. So at this point, 5 sees that its blocking set accepted X, so it just goes ahead and accept X as well. And we can also see that for node 4, the messages finally went through, and 4 accepted X as well. What about our nodes 6 and 7? So nodes 6 and 7, they also see that 5 accepted X, and 5 is a blocking set for 6, and 5 is also a blocking set for 7. So referring to our rule number 3 again here, accepted blocking set accepted, 6 and 7 can accept X as well. So at this point, everybody accepted X. So all the quorum slices accepted X, in which case we can proceed to our rule number 4, which is confirm if a quorum slice accepted. So everyone's quorum slices on the right accepted X, everyone's quorum slices on the left accepted X, so everybody can go ahead and confirm X. And at this point, it is safe to act on X. Great. So now that we covered statements and federated voting, let's actually see how those are applied to the Stellar Consensus Protocol. So Stellar Consensus Protocol is a two-phase protocol that uses federated voting to vote on statements. And the voting is on statements, and statements contain values. So for the Stellar network, values are transaction sets. The first step of the Stellar Consensus Protocol is the nomination protocol, which selects values to consider for a particular ledger. So it selects multiple transaction sets to consider for the ledger. The second step is the ballot protocol. And what it does is it actually attempts to commit those values which were selected during the nomination protocol. And it does so in two steps. At first, it prepares values, and then it commits values. All right, time for another diagram here. So we can think of the Stellar Consensus Protocol as the funnel. So at the very beginning, a node doesn't know anything about the state of the network. It does not know what its quorum slices agreed on. It's uncommitted. It may really vote for anything. It then goes into first step, which is the nomination protocol, where it selects a few valid values that it wants to consider. So it goes through the nominate phase, and it selects its candidate set. It then goes into prepare. Once it's selected a few nominations, it goes into the prepare state, where it attempts to commit those values. Alternatively, if it gets stuck, it can also accept what the blocking set accepted and proceed with that value. After that, after the prepare is done, nodes go into commit phase, where nodes attempt to prepare the values, attempt to commit prepared values, or they can again accept what the blocking set accepted. And then finally, at the very end, once the commit phase is done, this is where we know that the network has agreed on a single value, and so everybody applies the single value and the consensus is reached. So if you were to walk away from this talk just remembering one thing, this is the diagram that I want you to remember. Just high level, this is how Stellar Consensus Protocol works. It basically tries to narrow down all the possible values, and at the end, you end up with a single value, which everybody agrees on. And then you probably have guessed that this yellow step is what the nomination protocol does, and then the orange step is what the ballot protocol does for the prepare and commit. All right. Let's get into a little more detail about what nomination protocol actually does. So nomination protocol is essentially federated voting on statements such as nominate transaction set C. A node may vote for any transaction set during the nomination phase as long as it's valid. Once the node goes through federated voting on the particular nomination statement, and let's say that that nomination got confirmed, a node may add that value into the set that we call the candidate set. So the candidate set is basically just all of the confirmed nominations. There's an important variant here. A node stops voting for new values as soon as it confirms its first nomination. So a node may still accept and confirm values that it sees its blocking set accepting or confirming, but it may not vote for new values. And we will discuss a little bit more why this is actually really important in the next slide, but for now, just remember there's an important variant here that we do not vote for any new values as soon as you confirm something. And then finally, when we have those candidates, those confirmed nominations, we may select a single value, which we call the composite value. And at that point, we can start the ballot protocol on that value. So in a Stellar network, nodes select the biggest transaction set as the composite value. So if you have a several transaction sets in your candidate set, you just go by whichever transaction set has most transactions. All right, let's go over the ballot protocol. So ballot protocol, similarly to nomination, it's a procedure of federated voting on statements. And there are two types of statements: prepare transaction set X and commit transaction set X. So prepare verifies that everybody is willing to commit this value, that everybody's okay with committing it, while commit ensures that everyone actually commits the value and at which point it is safe to act on the value. The important thing here is that nomination keeps running in the background even when the ballot protocol is running. So you might have started the ballot protocol on a particular composite value, but nomination never really stops. So it may update the composite value in the background, and we will see why this is important in the next slide. All right, so why exactly do we start the ballot protocol as soon as we have a confirmed nomination? Why don't we wait for nomination to finish? So we know that eventually all nodes will converge to the same candidate set through nomination. And why do we know this? We discussed the important invariant a few slides ago that nomination protocol stops issuing any new votes as soon as it confirms its first nomination. Remember that it can still accept or confirm whatever its blocking set accepted or confirmed, but it may not vote for anything new. Because of that property, we can guarantee that eventually all the nodes on the network will converge to the same candidate set through nomination. But there's a problem. We don't know when. We don't know when that's going to happen. And so this is why we are starting ballot protocol optimistically as soon as we have our first confirmed nomination. But you might be wondering, like, can it hurt safety? Is it actually safe to do it this way? Is it possible that the network will end up with some different values? Actually, no. This is pretty safe. And there are two scenarios here. So best case scenario is, let's say we started with an optimistically prepared value, and let's say that the network actually agrees with that, and everybody ends up committing that optimistically prepared value. So it's kind of the happy path. Well, what happens if the things don't go so well? Worst case, a node might try to prepare a value, but it gets stuck because it doesn't see agreement of the other nodes on the network, and so it would time out. After it times out, it can either retry with the new composite value. Remember that nomination is running in the background and updating composite values, so we might end up with a new composite value actually. So it could retry with that new value, or if it sees that its blocking set made more progress and it accepted something or confirmed something, it can just switch over and vote for, accept or confirm whatever the blocking set accepted or confirmed. All right, so this was sort of a very brief discussion of the Stellar Consensus Protocol. I also encourage you to check out the blog post that we have. There is another demo in the blog post which actually shows how the federated voting works with both nomination and the ballot protocol. And it's very detailed, so I definitely encourage you to take a look. But for now, we're going to go over the summary. So remember that statement is a building block of consensus, and SCP uses federated voting to agree on different statements. Nomination is essentially federated voting on statements to select a small set of values to consider for a particular ledger. And the ballot protocol is federated voting, which tries to prepare and commit those values which were selected in nomination. And most importantly, SCP acts like a funnel by narrowing down possible values for nodes to commit. And with that, I want to see if there are any questions. All right. Do I have a choice to choose a threshold value for quorum slices? Yeah, that is a very good question. So you do, but the selection of threshold really depends on how many failures you're willing to tolerate. So generally, we suggest that for if you, for example, to add different organizations into your quorum set, you want a threshold of at least 67%. So then you can tolerate failures. But if you have nodes within your own organization, for example, then you can select a lower threshold. Like if you're running 3 nodes and they're all within the same organization, you can have just a simple majority, 51% threshold. But yes, short answer, you get a choice. When you configure your Stellar Core node, you may configure your quorum set however you want and select whichever threshold you want. But we generally recommend using the automatic quorum generation mechanism that we have built into Stellar Core, because it accounts for that 67%, and it looks at nodes within the same organization and it chooses simple majority there. So we definitely recommend going that route, because this way you're making sure that your configuration is actually safe and it cannot fork. Great. Any other questions? All right. Well, thank you guys so much. Thank you for watching.